In this lecture, we are going to learn about truss elements. As we know, a truss element can take either tension or compression. The difference between a one-dimensional element that we learned earlier and trusses is that the element of a truss has various orientations. So to account for these different orientations, the local and global coordinate system are introduced. Okay, so if this is my local global coordinate system and this is my truss element, so with two nodes, say 1 and 2, the local coordinate of this element is x dash. So x and y are global coordinates, whereas x dash is the local coordinate of the element 1. In the local numbering scheme, the two nodes of the elements are numbered as 1 and 2. The local coordinate system consists of the x dash axis, which runs along the element from node 1 towards node 2. All the quantities in the local coordinate system will be denoted by a prime, that is this dash. The global xy coordinate system is fixed and it does not depend on the orientation of the element. Okay, so say we take another element, this was element 1, say we are taking the next element, okay, this is element 2, and say this is node 1 and this is node 2 of the second element, and we are considering this as the local coordinate x dash. X dash will change for element 1 and 2, but the global coordinate system x and y remains fixed. Note that the x, y and z form a right-handed coordinate system with the z axis coming straight out of the screen. Okay, so in the global coordinate system, every node has 2 degrees of freedom. A numbering scheme is adopted here. A node whose global node number is j is associated with it, the degree of freedom will be 2j minus 1. So let us talk about element 1. We're talking about element 1, and if it has the node number j, okay, so this is the node number, its degree of freedom will be 2j minus 1 and 2j. Okay, so it will have it's a one-dimensional body, but it can have the displacement coordinates along x as well as y. So now this x dash, what we get here, it can be denoted in terms of the x and the y axis. So the degrees of freedom will be 2j minus 1 and 2j. So consider the node 1, so j equals to 1. So the degrees of freedom on substitution of j equals to 1 will be 1 and 2 into 1, that is 2. The global displacements associated with j, okay, so we have node number, degrees of freedom, and the displacement which is given by capital Q. Okay, so that will be q suffix 2j minus 1 and q suffix 2j. So in this case it will be q1 and q2. In red pen I am showing you here, so this will be q1 and this will be q2. Similarly, when we do for node 2, so when j equals to 2, it will be 2 into 2 minus 1 and 2 into 2, so this will be 3 and 4, so this will be q3 and q4. So this is q3, this is q4. So you have to remember this this formulae to find out, and this is a standard formula which is used for all the truss problems. Now let q1 dash, small q1 dash and q2 dash be the displacement of node 1 and 2 in the local coordinate system. Thus, the element displacement vector in the local coordinate system is denoted by q dash equals to q1 dash q2 dash transpose. In the global coordinate system, q will be given by q1, q2, q3, q4 transpose. The relationship between q dash and q is developed as follows. So we see the image on the left hand side of the screen. We can say that q1 dash is equal to q1 cos theta plus q2 sin theta. Okay, so this is q1 here, and q2 dash is given by q3 cos theta plus q4 sin theta. Now let us introduce the direction cosines L and M. So let L equals to cos theta and M equals to sin theta. So theta is the angle that this bar element makes with the x-axis, the global x-axis. These direction cosines are the cosines of the angles that the local x dash axis makes with the global x and y axis respectively. Now if we want to write these equations in the matrix form, we can write it as q dash equals to L into q. L is known as the transformation matrix because it transforms from the local coordinate system to the global coordinate system, and it is given by L M 0 0 0 0 L M. Now if we want to write the q dash equation, it will be now some formulae that we will require. This is theta, this angle here is theta, and this angle here is phi. So theta is the angle which the x dash axis makes with the x axis, and phi is the angle which the x dash axis makes with the y axis. So this is my global x and y, and this is along the x dash coordinate. Now we know that L equals to cos theta. We are given some coordinates. For example, here x1, y1, this is node 1, node 2 will be x2, y2. This will be the length of the element. We know that this distance is given by y2 minus y1, and the horizontal distance is given by x2 minus x1. We can call this cos phi, or we can call it sin theta. And the length of the element will be given by under root x2 minus x1 the whole square plus y2 minus y1 the whole square. So these expressions are required to obtain the data while solving problems. So the element stiffness matrix for a one-dimensional element, bar element, was given as AEL 1 minus 1 minus 1 1. Okay. A is the cross-sectional area, is a Young's modulus. Now, when we want to find the element strain energy in local coordinates, it is given by U suffix E half Q dash transpose K dash into Q dash. All this represents that it is in the local coordinate system. Substituting Q dash equals to L into Q in this equation, we will get UE equals to half. Now Q dash is L into Q, so if we take a transpose of that, the placement of the terms changes. So we can say that the strain energy is half Q transpose K into Q, where K is the element stiffness matrix in the global coordinate. Okay, so K will be given by L transpose K dash into L. Now substituting for L, we know that the L matrix was given by LM 0 0 0 0 LM, and so L transpose, we change rows into columns. Substituting all this, you will get a stiffness matrix in global for a truss element as follows: A E by L, L square, LM, LM, M square, minus L square, minus LM, minus LM, minus M square. This is the stiffness matrix for a truss element in global coordinates. So it is a 4 by 4 matrix. So if we see for a bar element, we had a 2 by 2 matrix. Okay, since the displacement was only in one direction, either positive x or negative x. Here for a truss element in global coordinates, we have 1, 2, 3 and 4 degrees of freedom. Okay, these are the 4 ways it can displace. So therefore the stiffness matrix is of the size square matrix of 4 by 4. Now if you take a look at this stiffness matrix, there's only 4 or actually 3 terms. It's L square, LM and M square. So the matrix can be divided as plus, minus, minus, plus. Thank you.